Hello everyone, my name is Brett Daly and welcome to today's webinar on induction coil design from Ambrell Corporation. Dr. Girish Dahake, Ambrell's Senior Vice President of Global Applications, will be presenting today. Girish has over 20 years of induction experience and leads a worldwide team of induction application experts. He holds multiple industry-related patents and has authored numerous papers and frequently presents at professional conferences on topics such as induction heating, nanoparticle heating, and heat staking. He holds a PhD in mechanical and aerospace engineering from the University of Rochester. Today's webinar will last approximately 60 minutes. Please enter any questions you may have into the chat or Q&A panels on your screen, and they will be addressed during a question and answer session that will follow the presentation. Thanks so much for joining us today, and now I'm going to turn it over to Dr. Girish Dahake.
Good morning to all who are attending us from the Americas, and good afternoon and late evening to everybody who is joining us from the rest of the world. So the topic today is a little different than basically talking about induction. We are going to spend focused effort on how are induction coils designed and manufactured. So typically, when you look at induction coils, we tend to assume that the people who are attending this webinar are already users of induction. You either inherited a machine, or you've sourced a machine, or you have seen induction being used. And more than often, it is discussed that the induction coil design is more of a black art than a science. Well, I have to be honest, there is some combination of both the art and the science that goes in the design of the induction heating coils. Today, we are going to talk about different design aspects of induction heating coils. We are going to talk a little bit about coil manufacturing. So for the do-it-yourselfers out there, you can actually use some of the training that you'll get through this webinar to actually try and make some coils. Obviously, you will have support of Ambrell engineers or whoever your induction heating supplier is, their engineers, if you are stuck with issues or problems during this design manufacturing process. So just to cover the basics, why does somebody use induction? Induction is highly precise in the way it heats, which means that it heats only the portion of the part that one is interested in heating. This is very different from other forms of heating like ovens or furnaces or flames. With all those other comparative methods of heating, it's difficult to pinpoint the heat. And usually, like in an oven or a furnace, the entire part tends to heat. So when you have those kinds of applications where you need to heat the entire part, then of course induction and ovens do the same type of job. But if you're looking to just heat a localized part or a localized section on a part, induction is superior in terms of its ability to deliver heat in a small area. Induction is also faster. Because we are trying to heat just a localized section of the part, we can get the heat in really quick. You can see on social media, YouTubes and Google that, typically you can see parts heat up to thousands of degrees in a matter of seconds. Well, that is easily achievable given the part lends itself to that kind of heating. And because we are traditionally heating just a section of the part or just affecting a small portion of the part, the amount of energy that is used with induction is much lower. This not only leads to quick heat up of the part, but also quick cool downs of the part, contributing to this entire efficiency debate. So the energy efficiency of induction is a lot superior. Just imagine parts being heated with a torch. How much of the heat that is emanating from the torch do you really think gets into the part that you're trying to heat? Or in an oven, if you're putting the entire part and let's say you're in a brazing or a joining type process, not only is the part going to heat up in its entirety, any holding fixture or device that is holding the part that gets put in the oven is also going to heat up. So the energy that's required in those kinds of applications is not just the energy that's required in the part, it's the energy of heating the air, it's the energy of heating the fixture, and it's the energy required to heat the entire part, which may not be required. Another big advantage of induction is that it's clean and it does not produce any residue because of the heating. The way induction works is through transfer of energy through magnetic flux. This type of heating is unique because it does not require a transfer medium to transfer the energy. And induction does offer extreme repeatability. Just basic induction system is able to repeat heating to precise temperatures cycle after cycle, day after day, month after month, and year after year. All these benefits of induction make it an economical heating process in the manufacturing industry. And that's why it's so important to understand every aspect of the induction heating process to be able to make a judicious, wise decision. So let's talk about what an induction system looks like. Typically, going from left to right, you can see that water cooling and electrical power inputs are typically provided to the induction heating power supply. The power supply is basically the engine that runs the induction heating system. It is basically a device, electrical in nature, whose purpose is to get the electrical signal from the wall and convert it into a high frequency signal. We'll talk a little bit in the upcoming slides as to what is frequency, but for the time being, you can just assume that its purpose is to basically generate a much higher frequency than what is available through the wall inside the induction heating power supply. The signal from the induction heating power supply is then transmitted through flexible cabling to a remote working head. And as the name signifies, it's the area where the work is being done. The remote workhead is connected rigidly or sometimes with flexible connections to an induction heating coil. Induction heating coils are all water-cooled copper tubes for the most part. I would have to guess that 99% of induction heating coils are water-cooled and copper tubes for industrial heating. The coil is also called as an inductor. So what does the coil do when you have a metal part either inserted in it or placed in the vicinity of this coil? So the induction heating coil produces an alternating or is given an alternating current, which means that the direction of the current in the induction heating coil switches back and forth. The switching back and forth is the frequency of the induction heating device. This is the frequency at which the parts are also going to be heated. The switching alternating current produces a magnetic field that also changes in direction every time the current changes direction in the induction heating coil. This change in magnetic field interacts with the metal part and produces eddy currents inside the part. Now, when you have currents that flow inside a part, they tend to produce heat. This is the heat that is seen in the part. So one obvious question would be, why does not the coil, which is also carrying alternating current, heat up and get hot? That is the reason why we have water flowing through the induction heating coil. So the water flowing through the induction heating coil keeps the induction heating coil cool, but is able to transfer the energy through the magnetic field to the part that is being heated. So the remote workhead that we just talked about is the C that is shown in the picture here. The L is the induction heating coil. The electrical characteristics of the C is given by the capacitance, which is given in farads, and the inductance, which is the L term for the coil, is called as the magnetic inductance. Inductance is a function of the way the coil is constructed. We will talk a little bit about how that changes in subsequent slides. But for the time being, the L and the C combination, because we have a fixed coil and we have a fixed capacitor, gives us a resonant frequency equation. And at this resonant frequency, there is minimum energy that is wasted inside the induction heating power supply or in the capacitor and the inductor network. But it's able to transfer maximum energy to the part that is being heated. Now, there are a lot of power supplies that are able to tune to this resonant frequency by automatically figuring out what's the C and what's the L, and the change in the C and the L as the parts heat up or as the energy goes higher. So the induction heating devices are able to automatically determine this frequency number. So even though this is the basic equation for the resonant frequency, the users of today don't have to really worry about calculating this if their power supply is able to determine this automatically. So what are this L and C for in this induction heating setup? Capacitance is basically denoted by C, and the capacitor is basically a storage device in the electrical circuit. The capacitor is a storage device for electric charge. Usually the simplest form of capacitor is two parallel plates that are separated by a dielectric, as shown in this picture. The induction heating capacitors are a combination of these conductive plates, but there may be hundreds or thousands of these conductive plate assemblies in one capacitor. This capacitance is a function that can be easily measured through the meters that are available today. The inductor, on the other hand, has a little more complexity to it. It is a function of the radius of the ID of the coil. So the loop that the coil makes is the radius. The length of the coil, which is the overall length of the windings. The number of turns, that is given by the small letter n on the right. And the formula for a typical simple solenoid, which is this round-shaped induction heating coil that you see most predominantly in documentation and in media, is a pretty complex looking formula. This induction can be calculated by this formula, but this formula does not hold for all different shapes of the coils. It's only good for a coil that is round and cylindrical in shape. For example, like if you had a 3-turn coil, let's say that has a radius of 3.5 inches, and its overall height was about 1.25 inches, the inductance of this type of a coil is 2.5 microhenries. Now, if you were to plug in these numbers, you will find that barring any edge effects or the losses that are in the copper tubes connecting from the capacitor to the coil, this formula holds pretty true. When you put an part inside the induction heating coil, the inductance of that entire circuit changes a little. So when you have to worry about all these small changes of inductance, it's actually beneficial to have the induction heating power supply automatically figure this out and resonate at the resonance frequency of the circuit. This induction or this inductance of the coil, like we said, is a function of R. So this equation in the center where L is defined as a function of R and L, you can see that as the radius of the coil increases, which means that the windings have more and more inner diameter, the inductance typically increases because R is in the numerator in that equation. As the number of turns of these windings increases, again, the numerator on this first equation increases and the inductance increases. However, as the length, the overall length of the coil increases, then the frequency or the overall inductance of the coil, I apologize, increases. The frequency actually decreases. So it's just a convoluted, really intermingled, involved equation. So, and this is an equation for just the simplest of the coils. Given that there are so many different shapes and sizes of coils, it becomes more and more difficult to calculate accurately what the inductance of the coil is. So we resort to the simple, lazy way of actually measuring the inductance using a inductance meter. These types of meters are pretty readily available. These types of meters are able to basically measure the inductance of the coil. The coil has to be disconnected from the induction heating power supply to get an accurate measurement. And then you can just basically plug in that resonant frequency equation to determine what the general resonant frequency needs to be. So this is the basic way how to calculate the inductance of the coil. The capacitance in the circuit in this formula is a discrete sets of values. So you can get different discrete sets of values and it's a fixed number. So given the L and the C, it's easy to calculate what resonant frequency your electric circuit is going to resonate at. So we need to now talk about how does the distance between the coil and the part affect the heating. Now we know that as the coil gets bigger or the inductance of the coil increases. But similarly, as the gap between the part and the coil increases, the heating decreases. So the tighter the part is to the coil, the better the heating is. Because the copper of the coil produces this magnetic field, and the magnetic field reduces in intensity as you move away from the copper tube. So that's why if the coil can be wound really tight to the part, then the efficiency of the heating is much higher. However, we do have electrical currents flowing through this coil, so we can't ever assume that this water-cooled heater, which never gets hot, is safe. you have to assume that it is unsafe because it has high voltage and high current in a lot of cases. Even though every manufacturer of today tries to make sure that the induction heating coils are safer and isolated from ground, there are older systems available where it's not the case. So you have to be very cautious and very careful around induction heating coils and assume that induction heating coils are electrical devices. So you have to be sure that you are not, if you're in the vicinity of the induction heating coil, right by the coil, working around the coil, you have to make sure that you have typical safety measures of either having mechanical isolation on the coil so you can't get too close to the coil, or have electrical isolation type built in, like light curtains or just basically light switches, so that if somebody tries to reach in and get in the vicinity of the coil, then the induction heating power supply can turn off. The big advantage with induction is as soon as that signal is interrupted or that circuit is interrupted, the induction heating power goes off instantly. It does not, however, cool the part instantly, so you might still be at risk touching a hot part or getting near a hot part. So needless to say, safety is of utmost importance when working around the induction heating systems. So what are the different types of coils that are available in the industry? Like we said, the most common coil that is available is a circular helical coil. It's easy to picture, it's easy to imagine, and of course, it's easy to build. And you can get pretty good repeatability by winding these coils on mandrels, which are basically wooden pegs, or really intricate machined pieces that give you repeatability time after time when you're winding the copper tube. The part has to be inserted in this type of coil to get the maximum or the optimal efficiency. In a lot of manufacturing processes, it's not actually practical to insert a part in a coil. So this type of coil, since it has very strong magnetic field on the ID, it also is more prone to heating fixtures and stuff. So when you design a holder to hold this part, you have to make sure that the holder is not robbing the heat that you're paying to put into the part. The other type of coil, if it's not a round coil, is called as a pancake style coil. Pancake style coils are flat coils which can be wound in just one plane, or they can actually change in the plane itself. So you could have a combination of a helical or a pancake type coil. The pancake type coil can be heated in a helical mode as shown in this center picture, where there's a glass tube that is inside this red induction heating coil, and parts are inserted through the glass tube, and the parts get heated and then they drop through. Otherwise, the pancake types coils are heated to heat flat parts, or in cases where a single coil may be required to heat multiples of parts sizes. The heat pattern is subject to the shape of the coil, to the spacing between the coil turns, and just the overall design of this coil. There is even one more option of making a coil, which is called as the channel type coil. This type of coil is actually able to heat parts traveling on a conveyor, for example. So it's easy to incorporate in a continuous type process where parts may be running along a conveyor or on a turntable, for example, and they have to be heated. The induction coil has loops on each end so that the parts can enter the coil and exit the coil. This type of coil is not obviously as efficient as the helical coil. Actually, helical coil is the most efficient. all other types of coils like this pancake or channel type coil is not as efficient. However, there are a lot of applications where a lot of parts have to be processed in a short amount of time, like in the manufacturing of fasteners. Fasteners hold all mechanical devices together, and there are millions and millions of fasteners made every day. So if you had to heat the fastener for doing some process on it, it would be advantageous to look at a channel type coil, even though its efficiency is a little lower, but it allows you to produce parts at a high yield rate. Then there are other types of coils like we show in this picture, a split helical coil, which is basically a circular coil, but the part that is being heated is placed in between the turns, and the axis of the coil and the part are perpendicular to each other. The reason why this type of coil might be used is the ease of access. The heat pattern, though, is really subjective to the type of part that is placed, that is being heated. If it's a round flat disc instead of this round cylinder as I show in this picture, then the heat pattern is very good. However, if you're heating a cylinder in this type of a coil, you will get two hot spots near the copper turns of the coil. So in a lot of cases, if you are stuck using this type of coil, you'd have to rotate the part so as to normalize the heat. There is another type of coil that is very convenient in manufacturing process called as the U coil. It's like a C, and it allows for easy integration because you can basically slide a part into the coil laterally and pull it out. However, as you can see from the pictures, the heat pattern that it produces is not really very, very clean. The heat pattern suffers because the magnetic field is the strongest near the copper turns. However, towards the open end, there is no heat being produced. So you can see that we are running this split helical type coil in this video, and the coins that are being processed in this type of an application work well, but it doesn't work well for a lot of different applications. There are other types of coils called as bore coils. So in this type of an application, you want to heat the part from the inside. Again, the making of the coil is not very difficult. However, the efficiency of this type of coil is not as good as if the part was inside the coil versus on the outside. Then on the right, we have some rectangular form types of coils where you have coils that are shaped. This coil is teardrop shaped because it has to give uniform heat to the part. The coil in the center is heating cylinder liners for an engine block preheating application. And on the extreme right, you can see that rectangular type coil is being heated with a coil that is oval in shape. So there is no real limitation to how an induction coil can be built. It is all based on what is required. In a lot of cases, we have limitations because of either of the manufacturing process or because of the layout of the parts, where multiples of parts have to be heated at one time. These types of coils are called as multi-position coils. And you can see an example of a multi-position coil in the top two pictures here. The coils are difficult to manufacture. It is important to make sure that the coils are similar from one position to the next, because if the coil shape varies or changes from one position to the next, then the heating pattern is going to be different as well. So a lot of times the coils are encapsulated in epoxies or ceramics, as you see in the picture on the right, so that the coil geometry can be sealed and frozen. There are a lot of ferrite type devices used in induction heating coils, but it's only when you're trying to solve a problem that's when you try to use ferrite in coils. If you have a problem that cannot be solved by conventional copper coils, then devices like ferrites are available to focus the heat or to take away heat from parts. So in this picture on the bottom right, the ferrites are on the outside of the coil, and the part that is on the outside, even though it's metal, doesn't heat because the magnetic field all travels through the ferrites. This shields the steel part on the outside, but allows one to heat parts on the ID of the part. So once you determine what the shape of the coil is, and here are still more shapes of coils than we just talked about, it is important to determine what are the basic characteristics of this coil. Is the coil really big? Is the coil really small? How repeatable is it? The picture on the bottom shows flexible coils where you can wind the coil around the part because the parts are so big or so cumbersome that a regular copper coil is not practical. So, induction coil design is basically up to an engineer's imagination as to how difficult or how easy it is. What you gain from experience is that you can actually use a simple coil to do a complex job. This is where the experience helps in, because a simpler coil is easy to make, it's easy to maintain, and if the coil is damaged, it's easy to reproduce. So even though the shapes and the sizes of the coils can be very intricate and complex, the goal should be always to design the simplest possible shape that can do the job. So once you determine what type of coil you're going to use, which is determined by the handling system that is being employed, the way it's going to heat, the type of metal, whether it's on a conveyor or on a turntable, then you have to determine what induction power supply you have before you can say, well, is the coil going to work? You have to basically figure out what's the material of the part, how much time you have to heat it, what's the heat zone requirement, and obviously the handling plays an important heating part. Then, given all this information, you have to then worry about, well, how much distance to keep from the coil to the part. If the rotary table or the conveyor is wobbly, then you can't have the induction heating coil really tight to the part. You'll have to have a coil that is a little loose to the parts. And just the way the coil is then going to be manufactured. So let's talk about the distance of the part. Why would you want to change distance from the part and not just have a very tight distance from the coil in all cases? There are a lot of applications, like in high temperature applications, where one may not want to have the copper tube too close to the part because the heat from the hot part might affect the copper. Or as you can see, the picture on the extreme right shows a glass tube inside the induction heating coil. Now you have to then allocate space for that glass tube to slide in easily inside the coil. In this example, as you can see, there's like multiple coils being fed by multiple induction heating power supplies. So the handling system, tolerancing, all determines how repeatable the coil has to be, how accurate the coil has to be, and is the fixture able to accommodate the way the parts are being held and being heated. Once you determine what type of coil or how many turns you need, the way you wind the turns has a really big bearing on how the heat is being produced. The 4 pictures in the center of your screen shows the same 8 turns of a copper tube being wound in different manner to provide different types of heat patterns. This is basically the way the coil turns are wound, the spacing between the coil turns. You can basically affect the same number of turns to give you differences in heat. The picture on the bottom right shows a very unique looking part that has intricate geometries on the same part. And then the induction heating coil has to be designed to do the same, to give it uniformity of heat. Picture on the top right shows a stepped induction heating coil, where the turns of the coils have a step in it to go from one turn to the next. This gives us a very nice uniform heat zone on the part. There are a lot of other tricks of trade in induction heating coil design where you can have the same coil heat a metal rod but not heat a metal plate just very close to the coil on the extreme right. But on the extreme left, you can see that that same coil is just heating that steel plate where it starts to even glow. So all these things are all available to an engineer when you're looking at designing induction heating coils. Well, then once you determine what shape of coil you need, you have to determine what size copper tube do I start to use. If you go to a regular hardware store or go online to look for copper tubing, you will find that copper tubing comes in all different shapes and sizes. You can find round copper tube, you can find rectangular copper tube, you can find square copper tube. Well, when do you use which? In a lot of cases, the amount of or the number of turns that you have to fit in an area or in a length determines what shape of copper you use. So the picture on the extreme right top shows a rectangular copper tubing coil because we had to cover up the entire length of that heat zone with a certain number of turns to get the inductance to match together. Well, the picture on the bottom left is totally opposite. We needed more turns in the coil to fit in a certain area. So we wanted to have as many turns as possible. So we wanted to use a smaller copper tube. Now, a smaller copper tube obviously will not flow as much water as a large copper tube. So a lot of times, water bypasses are incorporated in sections of the coil so as to have cold water being supplied to the induction heating coil. If there were no bypasses and you were trying to run high power and high currents through the induction heating coil, the water flowing through the small copper tubes is going to heat up and basically boil inside the induction heating coil. Well, if the coil is not cooled because the water is heating up, the induction heating coil will heat up and basically burn and melt. So it's important to determine how many turns you need and what size of copper tubing would be required. Other considerations that are used before the coil can be actually manufactured is, well, how far is the induction heating coil from the remote box or the induction heating power supply? If there's longer lengths or if there is lengths that have to be incorporated, then copper tubes have to be wound or leads have to be pressed close to each other, because any run of copper that is not doing active heating is a loss to the system. In some cases, you actually want to incorporate the loss in the induction heating coil feeds. Those are shown on the bottom part of the picture of your slide. We actually have sacrificial coils sometimes to match the inductance so as to resonate the coil on the induction heating power supply. So if the coil had only a single turn, or if it was a very tiny coil, you may have to incorporate some extra matching coils, as they're called, in the path of the copper tubes to aid the entire system to run at the frequency of choice. So there's a lot more to induction coil designs than just winding the copper, as you see. In a lot of high temperature applications, like we talked about, there is a requirement to have insulation between the coil and the part. This preserves the heat that we are putting into the part. And the advantage is that the heat is being prevented to escape to the environment. Disadvantage is that if you're looking to measure temperature, you have to design in features like peepholes or openings in the refractory to give you the measurement of the temperature. So there are a lot of insulations available. In the industry also, as you are manufacturing, you know that you're going to be moving the parts in and out of induction heating coils. So the fixturing and the handling becomes really important as well. You can see that the fixture that holds these parts that you see in the picture, these are rotors for electric motors. The fixture has holes drilled in it. The fixture is basically a rod, but to not have the heat just run down the rod or the tube has holes put in it so that it basically stops the flow of heat down the rod and basically preserves the heat that we are being put or that we are putting into the system. This is obviously an example of a multiple position induction heating coil, and all 12 locations are being fed by one induction power supply. So the parts come in and out depending on the heating time that is pre-selected. There's a robot that actually picks the parts out once they're heated. So it's a pretty elaborate setup. An induction system allows one to have this kind of complexity in the heating process. Imagine if you had to do the same type of process with a flame or a furnace. There'd be so much wasted heat around that it would be impractical to use some of the materials that we are using to hold the part and just all the electronics that's near here. A lot of times there has to be a balance that needs to be struck between the efficiency of the coil and the practicality of the coil. So that's where the coil shapes start to deviate from the simple helical. Here you see that it's a diamond-shaped coil because the handling system for this particular device, which is making wire nuts, has two rotating rollers that are running through the coil. Well, not only are the rollers rotating through it, the customer required that if there was any wire nuts that fell in the coil, they would be easily visible and be able to be taken away out of the coil so that it doesn't sit there and burn. That's why the coil, rather being just an oval, had to have this dip in the center at the bottom so that the any rogue parts or any parts that didn't go through the feeding mechanism correctly could be taken away. All these things, it's always a balance between the efficiency of heating versus practicality. Obviously, as we make the coils bigger or we add more space in the coil, the efficiency of heating goes down, but the practicality of heating goes up. So there is a balance there that has to be struck in for every typical case. So let's talk a couple case studies. We have this application where we have to heat this irregular shaped metal part, has to be heated to about 1000 degrees centigrade, which is 1800 degrees Fahrenheit, for a brazing application. The customer had requested uniform heat around the whole length of the part. and the part is magnetic steel. So the first obvious solution is to just have a coil or incorporate a coil that is just circular with uniformly spaced turns. Well, the reason I'm showing this is because that didn't work. So what we had to figure out is, well, if you had one fixed diameter of the induction heating coil, could we achieve uniformity of heat in the part by just changing the distance between the coil turns? So you can see going from right to left, where the part diameter is the smallest, the coil turns are the closest. The closeness of the coil turns makes for a stronger field and delivers more heat to the part. So even though the heat pattern that you see is not totally perfect, it's within the tolerance specification that the customer required. And this is where, like I say, knowing that you can just change the coil turns spacing to give uniformity of heat makes for a much easier coil design than to individually change the coil turn diameters as you change the diameter of the part. Because that type of coil will be a very long drawn engineering project if it has to be run like that. There was another case study here that came to us where a customer wanted to heat two metal parts, the shapes shown in the picture on the right, before a aluminum die cast operation. Temperature was not too high, but the customer wanted as uniform a heat as possible to be able to then put these parts in an injection molding machine. Well, when we tried typical simpler type of induction heating coils, you can see that the heat pattern was not uniform. The top of the large part was hot, but the bottom of the small part was hot. And it was not possible by just moving the turns around to get the uniformity of heat. We therefore went through an extensive coil design where we went through iterations of coil designs and finally ended up with a coil design that worked. And you can see from the picture at the bottom right that this induction coil ended up to be a pretty crazy looking coil. I have to say here that not all coil designs are this complex. Just wanted to show you how complex it can be for some cases. Well, when this complex type coil was then put on the machine, you can see that the heating pattern achieved on the part was pretty uniform. This was meeting customer specifications and allowed us to be able to heat parts in the customer's environment with their handling constraints and with their fixturing constraints. We'll talk about one more case study before we move on to the other aspects of induction coils. So this customer wanted to heat aluminum motor housings, which are these aluminum boxes, for lack of better term, and the steel motor cores that you see on with the wire sticking out, all with one coil design. They did not, or they were not in favor of changing coil designs from one part to the other. So when they switched parts, they did not want to change coils. Well, as you can imagine, this defeats, or this goes against all the basics of coil design that we just talked about. You can't have a constant coupling distance, you can't have a constant coil turns, everything is out of whack. However, the biggest advantage we got was because of the material of the part. Aluminum is such a good conductor of heat that even though we designed one large induction heating coil to heat the largest of the part, it was still able to heat the smallest of the part because the induction heating power supply was automatically able to tune and resonate and deliver energies to the small part as well, not at utmost efficiency, but still able to do the entire assembly or entire operation for the customer with one standard coil design. This was challenging. It took us a couple tries to get the coil design right, the spacings between the turns right, to get the heating to be uniform for not only the large part, but also the small part. So once you design the coil in your mind, you draw it up, sketch it up, then comes the fabrication type process. Well, you need to have obviously the copper tubing that you're going to use. There are different types of thicknesses of copper tubes that are available as well. And one might ask the question, well, which copper thickness do I use? You need to have the connection blocks that connects the copper tube to the remote working or heating head. And then you obviously need to have either fittings or brazing alloy to connect the two together. The reason why copper tubing wall thickness is so important is that given the frequency of operation, you can either utilize the entire cross section of the copper or not be able to utilize the energy that is able to be delivered by the induction power supply if the wall thickness of the copper tube chosen is not correct. So for higher frequency, rule of thumb is for higher frequency power supplies, thinner wall sections or thinner cross sections of copper walls are able to be used. Typically for lower frequency operation in the 310 kilohertz type ranges, you need a little thicker copper tube because the current travels over a deeper case depth. And this does make for optimal use of the current process. Otherwise, the current cannot run through the copper thickness because the wall thickness is not thick enough. So these are some basic considerations. Then to wind the coil, you can incorporate either wooden mandrels, shaped wooden mandrels, or milled shapes where you can lay in the copper tube to build the coil, or you can have automated setups like shown here to wind simple round type coils repeatedly. So this customer, for example, had ordered 50 induction coils from us that were all round. So it's not a very difficult shape. But when an operator has to wind the copper tube by hand around a wooden mandrel, it's hard to put the same type of force and pressure on the copper tube. And then when the copper tube is wound, there's differences in spring backs that are achieved. So that's where a machine like this is very helpful to wind the copper tube and give repeatability in the coil manufacturing. Once the coil is made, you have to determine and you have to then basically allow for what kind of environment is it going to be in. Is the coil need to be encapsulated in ceramics? Does it need to have support mechanisms on the side, like studs as shown in the top right picture here to hold the turns in place? Because if we've spent all this time and effort designing a coil with variable turns spacings, you want to seal in those turn spacings. So an easy way to seal in the turn spacing is by encapsulating the coil. But as you can see from the pictures at the bottom, it's a pretty involved process to encapsulate a coil. And this coil is just a circular, simple design. If you had an elaborate big coil, the encapsulation becomes heavy, the encapsulation becomes pretty unmanageable. So studs are incorporated with ceramic insulation in a lot of cases. And that choice has to be made whether it's a good fit or a bad fit for encapsulation. What else goes into the coil design process? Well, there's a lot more steps behind the scenes that happen that go in a coil design process. Because the induction heating coil is copper tube, there are times that induction heating coils get damaged or broken, or a machine runs into it, or sometimes the coil just doesn't work because somebody forgot to turn the water on or bypass some of the safety devices, and the coil is no longer usable. Well, to make a new coil that is exactly the same, you need to have like an engineering drawing through an AutoCAD or some modeling process, so that you can then go back and reproduce the same coil. Well, we had cases where we've shipped induction heating coils in the past, and by the time UPS or FedEx or some shipping department or shipping company deals with the boxes and tosses them around, the way the coil left our factory is not the way it arrived at the customer site. So we actually have to put our extra effort has to be put in the packaging of the induction heating coils once they're built, so that the way they leave our factory is the way they arrive at the customer site. All this is all behind the scenes stuff that happens in the coil design process. And then finally, there's just a conclusion slide. There's a lot of science behind the induction heating coils that is not typically evident. The induction heating coils are custom designed for efficient heating. Even though the perceived value of an induction heating coil is just the cost of the copper tube. I've heard a lot of people complain and moan that it's $20 worth of copper tube and fittings. Why does the coil cost so much? It's all this back end processes, all the hidden processes that are in this design process that basically lend or go into figuring out what a coil is costs. Because a well-designed coil offers the advantage of longevity of the coil, the repeatability, heat pattern, and the ease of use, which would be lost if the coil was not designed properly. And finally, the induction heating coil is only as good as the induction heating power supply driving it. So you could have the best possible coil design, but if the induction heating power supply is not up to par, then you may not be getting the benefit of this automatic frequency tuning and automatic load matching that is available in today's induction heating power supplies. So with this, I'd like to conclude our presentation today, and we'll open up for some questions.
All right, thank you, Girish, for that informative presentation. If you haven't already entered questions into the chat or Q&A panels, please do so now. Also, when you leave the webinar, a survey should come up, and we'd appreciate your feedback. Now we'll kick off the Q&A. The first question that we had was, how can you theoretically calculate the inductance of a pancake-type coil? Is there any formula? And if yes, what is the formula?
So obviously, there is a formula for calculating the inductance of a pancake-style coil. I cannot remember the formula. It is pretty involved because it has to deal with the opening on the inside of the pancake coil, the distance between the copper turns, and the overall diameter of the coil. There is a formula out there in literature that we can share. So if you would be so kind as to email us the question, we would be able to send you the appropriate link to find the formula.
All right, thank you, Girish. Our next question is, how many cycles are there before a coil burns up?
So an ideally designed induction heating coil should never really burn up. If it has enough water flowing through it and the design is correct, the coil should not burn up. However, there are a lot of applications, like in the heat treating industry, where there are such high currents flowing through copper coils that it leads to the fatigue of the copper tubing, which means that the constant on and off of the induction heating coil basically fatigues the copper, and the copper basically gives because of this repeated on and off of the induction heat process. those types of coils have limited life cycles. I have seen coils that have only 5,000 heat cycles on them because they do such a incredible job of delivering high energy in small areas. But then there are coils that we've sold that have run continuously for hundreds and thousands of cycles. So it's actually very subjective as to how long an induction heating coil should run before it burns up, because it's a function of how much power is being put in, how much current is flowing in the coil, how many cycles are being run, and whether there is adequate water cooling available. Thank you.
All right, and our next question here is it practical to apply the coils in a heated roller process?
So induction heating coils are able to heat any metal that is in the vicinity of the copper coil. It can be a roller, it can be a cylinder. So in a low roller type process, we would imagine an elongated long coil that is able to heat the roller, and the roller is turning in front of the coil. That type of coil works actually very well. We supplied a system like that to a customer that was heating steel belts on the rollers. So it is possible to heat rollers with long elongated coils that cover maybe a quarter of the roller circumference.
All right, and our next question is, can you suggest any material which could be used to fix two pieces together when brazing? We are brazing carbides to steel bodies and need something which would keep the carbide in place while we heat to 2000 degrees Fahrenheit. This implies to me it needs to be something which is not easily heated by induction and which has a high thermal resistance. Ideally, they would be reusable. I saw ceramic as an option in your presentation, but I fear the manufacturability of that is insufficient for our usage.
Very good question. So without knowing all the details as to how big the parts are and what is the typical problem that is being faced, ceramics obviously are not very robust for that kind of thermal shock, because you may have flux in the area, you may be having handling issues in the area, so ceramics may not work. Sometimes materials like titanium or graphite are used to be fixturing devices, because the braze alloy does not stick to them. So if it is able to be used, you could use titanium rods or titanium push devices to hold the carbide in place. Because even though the titanium might heat from cycle to cycle because it's in contact with the metal, it will not stick to the braze alloy. So if you might have titanium in the vicinity, and it will work for some cycles. I can't say that it is going to work forever, but it will allow for a better performance than a ceramic. We've seen in some cases customers will use graphites. Graphites are inexpensive, but they're consumables. So those types of devices are also able to be used in a brazing type application.
All right, and our next question is there a formula to determine the dissipation of a vertical coil from loop to loop?
I'm sure there is, but I apologize. It probably would be a good question for a simulation package to be able to figure out what is it exactly that you're trying to find out. If you're looking for magnetic flux intensity, yes, there are software packages out there that will be able to give you the flux density at different locations inside an induction heating coil. If you're looking for the amount of heat being produced in a metal part, a lot of times it's cheaper and faster to do a quick trial to be able to determine what kind of heat is being produced, because eventually all induction heating coils have an output that is in the form of heat. If you're worried about the heat, then what better than to just measure the heat it's producing? However, there are software packages available out there that will allow you to calculate the magnetic flux and the intensity of the magnetic field inside various locations of the induction heating coil.
All right, thank you, Girish. And our next question is, how large does a part have to be to render induction heating impractical?
So this is a good question. I have seen coils large enough where human beings actually walk inside the coils. So depending on what the application is and what the requirements are, there is not really a physical limitation I can picture for the induction heating coil. Certainly, it's a case-by-case basis. So we would recommend that you should run your individual case by an engineer to make sure that it is feasible. But there is no physical limitation to how large an induction heating coil can be. For example, there is a flexible induction heating coil that we make in 100-foot length. Now you can wind 100-foot length a single turn around a big part. Or you could gang up a bunch of 100-footers around a big diameter part to give you a big induction heating coil.
All right, and our next question is, how can you figure out or find the power loss with an induction coil?
Very good question. So typically, the correct way of doing this is to figure out how much energy is being put into the part over one heat cycle, for example. Then figure out how much energy was used in that heat cycle from the wall. The difference in the energies is going to give you the energy that is consumed inside the induction heating power supply and the coils. That is going to give you the best possible answer to your question. However, if you just want a rule of thumb type energy transfer into the part, you can a lot of times read the power display running a induction heating coil with no part inside the coil, and then running the same cycle with a part inside the induction heating coil. And then the difference would tell you how much energy went into the part versus how much energy was used by the induction heating power supply to create the magnetic field.
All right, and our next question is, as for the heating characteristics, can we say that induction heating will heat, say, a plate from one side more uniformly than resistive heating? And will the temperature gradient set in vertically be less in induction?
So this is a great question. However, let me answer the two parts of the question one by one. Resistance heating is a good way to heat parts. So I can't say that induction is going to give you a better heat pattern than induction heating. So a well-designed system, no matter whether it's resistance or induction, should be able to give you similar heat patterns. Now, induction heating differs from resistance heating in the fact that induction heating heats into the depth of the metal that is being heated. So in a pancake style coil, we actually heat into the depth of the metal plate. So depending on how thick the metal plate is that you're trying to heat, the perceived heat pattern on the top surface can be really good looking or really bad looking. So you have to determine that based on the thickness of the part. if there is some conduction time, or if the lateral conduction is better in the metal, then the heat pattern on the top looks really nice. So it is again a very subjective evaluation, but I can't believe that resistance would not be able to give you the same type of heat pattern.
All right. So our next question is, what is the ideal frequency for induction heating? And is there even a range? And can you make a comment about induction levitation heating? How does it work with non-ferromagnetic materials?
Good question. So there is no ideal frequency for induction heating. Typically, the rule of thumb is if you have large parts to heat, you tend to gravitate towards lower frequency induction heating power supplies. When you have small localized sections to heat, you tend to gravitate towards higher frequency power supplies. And the reason is economic. It's cheaper to make lower frequency power supplies that are able to deliver a lot of power for large part heating. So that is the answer to your first question. The levitation phenomena that is observed with induction heating coils is because of the magnetic flux that is produced by the induction heating coil. Any metal part that is put in that magnetic flux wants to go away from that magnetic flux. It doesn't matter what that part is, whether it's magnetic or non, the interaction is similar. It is more pronounced in magnetic parts, not as pronounced in non-magnetic parts. So that's why it doesn't matter what the material makeup is, all metals tend to levitate right near the induction heating fields. And given a strong enough magnetic field, the metals will actually float in air.
All right. And our next question here is there any way to calculate the coil's capacitance without use of an instrument, for example, maybe a form?
The coil has the inductance, and you can calculate that by using the formulas or by measurement. Those are the only two ways I know of calculating the inductance of the coil. The capacitance in the remote workhead should be stamped, should have stamped values on the side, because they are pre-manufactured prefab pieces. So they are discrete values, so you can measure or read the capacitance of the box itself.
All right, thank you. Our next question here is, how does coil part inductance change when materials change? For example, if trying to use a coil designed for steel to heat aluminum instead, and vice versa.
Great question. Our experience has shown that when you put an aluminum part inside the induction heating coil, the inductance of that whole setup actually goes down. So the frequency goes up. With the steels, for example, that are not highly conductive like aluminum or copper, there is not as much change in the frequency. So the circuit is different. And this is where the automatic tuning feature comes in so handy, that we don't have to worry about it. The induction heating power supply automatically detects what the material makeup is inside the coil and automatically resonates to the resonance frequency to deliver the energy.
All right, thank you, Girish. And our next question is, how do you find the optimal pitch distance between the induction coil?
So like I said, the output of the induction heating coil is the heat pattern that is produced on the part. So to determine the optimal pitch, we will actually start the induction heat, observe the pattern of the heat it's produced, and then where you have the requirement to have higher heat, you would then turn the induction heating power off and then tighten the pitch. And this is basically an iterative process that has to go back and forth between heat cycles to be able to determine what the optimal pitch is of that induction heating coil turn.
All right, thank you. And our next question is, how do you make sure that the cooling system works efficiently?
So a well-designed system, like the cooling system, should have the capability of generating enough flow and pressure and be able to maintain the temperature of the water. So modern day coolers have the ability to give you a readout of the temperature, and you can actually get a readout of pressure and flow if you are having any issues with your current process. There are meters readily available that are not very expensive to be able to do that. So if it's designed correctly, it should be able to provide adequate water cooling to the induction heating setup.
All right, and our next question is, what is the best way to determine if the coil design and size will be sufficient for an application prior to purchasing one?
So there are a lot of companies that will offer free feasibility testing. Our company also offers the same, where we have an applications lab where we can actually run your process on a lab style basis to get a good feel for what the process is going to entail. This allows us to get an idea of what type of coil would be needed, how efficient the system is going to be, and then calculate how much power is needed. This would be then translated into a quote from the manufacturer, and then you can source the power supply.
All right, thank you. And our next question is, can a specific temperature be held by pulsing the power supply?
The answer to that question is yes. You can source or you can pulse the output of the induction heating machine to give you the right temperature. It is not very common in the industry because there are better ways to do the same process through a PID type control loop, where the induction power supply is just turned on and the output of the induction machine is changed, because it can be done much more rapidly and much more efficiently rather than turn the induction machine on and off.
All right, thank you, Girish. Our next question is about coil design and load matching. How the number of turns affects the frequency and the inductance.
So typically, the larger the number of turns, the frequency goes down, because the inductance of the coil is much higher. The larger the number of turns, if it can be fitted around the part, lends to a more efficient process. So there's always a give and take between how many turns you are able to put in versus what the efficiency of the system is to be able to get the best induction setup. Ideally, if you could put 1,000,000 turns, you'd have the best type of heating, because you'd have such a good transformer effect between the coil and the part. But it's not practical. So that's where you need to know what induction machine you have, how easy it is to change stuff, and how well its automatic tuning works to be able to then match to the induction heating coil that you designed.
All right, and our next question looks like a follow-up to an earlier power loss question, and that is, what are the factors that affect power loss in an induction coil?
So in an induction heating coil, obviously the biggest power loss is the distance between the coil and the part. The farther the coil is from the part, the harder it has to work to deliver the energy. In some cases, the heat from the hot part comes into the cooling water of the induction heating coil. So that affects the heat loss from the part. So those are the cases where we would employ insulation between the hot part and the coil, but try to make the coil still as tight as possible, because that's what gives us the most efficient coil design.
All right, and I've got another follow-up question. The individual says, thanks so much. So if I got it right, you can technically levitate on any coil if they produce a strong enough field?
Yes, there is a magnetic field produced by any coil. So given a strong enough magnetic field, any material would move away from the coil. Whether it levitates and floats is a function of the shape of the part. So if you just Google or search for levitation heating coils, you'll find that they're designed in a particular manner, because the coil turns are not only used to float the part, but the coil turns are also used to basically not let it just fall off the coil. So the two turns of the coil, or the turns of the coils, are wound in opposite directions to basically locate the floated part in between the two sections of the coil.
All right, and our next question is roughly how much power is required to heat a 12-inch OD pipe to a semi-liquid state?
So the critical piece of missing information is how long you have to heat the pipe. If you have, let's say, a minute to heat, 12-inch OD pipe, if I were to assume a half-inch wall or something, you could get it to that 2200, 2400 degrees temperature with about 100 kilowatt power supply. So that'd be like a minute to 2 minutes type of heating process. Because the temperature is so high, you want to make sure that you have good radiation control, you have good insulation on the part.
All right, and our next question is how can you find the resistance of a copper coil at high temperatures?
So the resistance of the coil is only a function of the temperature of the copper. Because there is water flowing through the copper is never getting hot. The part is getting hot, and its electrical resistance is increasing. So there is charts, people have done these types of tests, and you can find the data in literature of electrical resistance of different metals at different temperatures. So that's where I would point you to get the electrical resistance.
All right, and our next question is how do you control the power input cycle to output a specific temperature to heat the part?
So there are specific controllers available that have sophisticated logic working in them through a PID type loop that can control the output of the power to just give it more or less power depending on what the temperature feedback is telling it. So these types of controllers are readily available. They are not very expensive. They do require you to have a measurement of the temperature, though.
All right, great. Thank you, Girish. And I think that'll wrap up today's presentation. So thank you, everyone, for joining us today. We hope you found the webinar to be informative, and be on the lookout for future webinars from Ambrell. And as always, please let us know if there's any way in which we can help. Thanks again, and have a great remainder of your day.